So good morning, everybody. My name is Ludger Kemper. I'm a sales application engineer at Light Vision Technologies, and I want to show you today some information for imaging beyond the visible. I want to show you the shortwave infrared, something about the shortwave infrared technology, difference between shortwave infrared and CCD and CMOS cameras. I want to show you some ideas of applications and benefits of shortwave infrared, especially in the semiconductor industry, the photovoltaics, glass industry, and also plastic sorting with hyperspectral imaging, and also a conclusion of that. What is shortwave infrared? So we have, the normal CCD, CMOS cameras or sensors, and also the near enhanced CCD and CMOS sensors are sensitive in the range of 400 up to 1,000, 1,100 nanometer. And you see here the images, that's the normal images at the visible range. We also have then these standard InGaAs or indium gallium arsenide sensors, what are sensitive in the range from 900 to 1,700. And also in this range you have two kinds. You have visible extensions in these cameras, and also you have the sphere extensions up to 2.5 micron. And here you see then typically images of the sphere range. You see there is some plastic what is transparent in sphere. You can have there water in that. Water is black at 1,440 nanometers. And so you also can see then, you can detect bruises in fruits, because that enhances then the water in that. And you have also on documents like here the 50 euro currency, you have there ink what is transparent or what is visible in sphere, and so you can detect then the money for it. And what is difference between sphere cameras from a classic for the classic machine vision? So these cameras, first of all, we have the indium gallium arsenide detector in that. That is sensitive between 900 and 1,700 nanometers. There is very high complexity level in the production process, and so therefore you have more effect pixels in this technology than you have in the in normal CCD, with normal CCD sensors. And you have non-uniformity pixel behaviors, and you have in InGaAs sensors, you have on higher dark currents than in CCD and CMOS. Due to the high current, dark current of the InGaAs sensors, cooling is necessary, at least a temperature stabilization so that you have stable conditions. But you can also have cooled it down, more down, to have higher integration time. And for that, you need more intelligence inside the camera. You need advanced image correction features. You need inside the camera the non-uniformity correction, the defect pixel correction, and also a background correction. So when you see the structure of a typically sphere camera, you have the sphere optic in front of that, sphere optimized optic. You have also filters in that for some special applications. You have different InGaAs sensors with different resolutions. You have the cooling. You have then the pre-processing functions and the electronic, and you have then different interfaces with the I/O control and that. I want to show you the effects of the cooling and of the more intelligence. So when you see here, that is a typically raw image of an InGaAs sensor. At a temperature, sensor temperature of 40 degrees with 100 millisecond exposure time. And so if you cool down the sensor then to -5 degrees, for example, then you lower the dark currency so that you are able to have then also lower exposure times. And here you see inside the image, you see then the fixed pattern noise in that image, and you also see here some red pixels, white pixels, and also dark pixels, what you see in there. And if you now use the non-uniformity correction, then you have no noise in the image and no fixed pattern noise in the image. And on the other hand, when you now have done the defect pixel correction, you also correct then the defect pixels inside in the image there. And so that is the functions that are necessary for InGaAs sensors. Here you see an overview over different applications where you can use sphere cameras. You have in the industrial machine vision, you have the normal semiconductor industry, photovoltaic industry, also chemical, so gas, plastic, and fall detection. Pharmaceutical, you have it in the quality control there, glass production, agriculture, and also in food. In scientific and medical, you have microscopy application where you also want to see some details in the sphere range. The hyperspectral imaging to detect characteristics also in sphere, laser beam profiling, airborne remote sensing, and also in art inspection you can use sphere cameras. In the security and traffic range you have applications, surveillance application, vision enhancement, especially night vision. You can use sphere cameras and also in homeland security. I want to show you only some special industry where you mostly use the sphere camera. There is a semiconductor industry. You have there the sphere camera for silicon crystal and ingot inspection, so the whole blocks. You can use it for wafer inspections, wafer level packaging, and photo emissions microscopy, and also photovoltaic. You can use it in the sphere camera in this one. And what makes sphere so special for the semiconductor inspection? So because you have here the quantum efficiency of the CCD and CMOS near enhanced cameras, so you see then the sensitive up to 1.1 micrometer or 1,100 nanometer, and the sphere camera is sensitive from 900 up to 1,700 nanometer. And above 1,100 nanometers, silicon becomes transparent. So that is the reason why you can look through the ingot and see then inclusions in the ingot. On the other hand, you have then in the upper range of the CCD CMOS sensors, at 1,000 nanometers, you have in the InGaAs cameras you have 76% quantum efficiency, and on the CCD CMOS you can have then 3% only there. And you can use this the sensitivity of the sphere camera. You can use that for luminescence imaging. So when you and to identify non-uniformities in the silicon wafer or in the solar cell, forcing it to emit light. So you can use, there are two different methods. You can use the electroluminescence method, where you put voltage on the wafer, so to eliminate, so that the wafer emits then light in the sphere range. And on the other hand, you can use photoluminescence method, where you put light on it with a laser, for example, 800 nanometer lasers, and then also the wafer or the silicon emits then in the sphere range. And you see here a typically silicon effect curve. You see here two effects, one at about 1,100 nanometer, and also a defect band signal on 1,550 nanometers. And you see here that is not a small peak, but the sphere camera has there a good quantum efficiency, so that you can detect this signal in sphere very fast. But also the signal goes down to 900 nanometers, so you can also detect the signal here with a normal visible camera, but therefore you need then long exposure times on seconds instead of milliseconds with a sphere camera. So you always have here two, when you have time, you can use a cooled CCD camera for with long exposure time. If you are in the wafer production where you need 6 wafers per second and have to control 6 wafers per second, then you have to use sphere cameras. So then you can, so what I already told you, you see here some images where you see then there are some micro cracks in the solar cell and so on, and you see the efficiency of the solar cell by this luminescence method. This typically peak emission wavelengths are for different materials. You have when you have cadmium telluride material that emits at 800 nanometers. Therefore you can use CCD cameras. It's in the visible range. Silicium or silicon is at 1,107 nanometers. So that is what I showed you before. And we also have then this copper, indium, gallium ditheliide that emits at between 1,300 and 1,700 nanometers, or this copper, indium ditheliide that emits at 1,300 nanometers. For these two, you can only use sphere cameras to detect the signal. You can't use CCD camera. That's normally used in the thin film solar cells, this material. So that was semiconductor industry. So coming to the glass production, their sphere is very useful for the hot end glass inspection. When the bottles are coming out with a high temperature out of the oven, you can't use visible for that to really detect some difference in that. You can't use or you can use thermal cameras, from 8 to 40 microns, but there you can only see the surface. With a sphere camera, you can look through glass, because glass is transparent up to 2,500 nanometers, and you can then inspect both sides of the bottle with one in one shot. You can see there the temperature difference and that at that point, and you can see any defects, major defects in the glass. You can see when there is something in the bottle, you can see with a sphere camera, and then you can detect them from the bottles very early and then recycle that direct and not cool that down really to lower temperature, and that then takes too long to smell it again. You also can use the sphere camera. I mentioned that you can make temperature measurements in that range, and based on the Planck's radiation law, what you see here is that as warmer the material, at lower the wavelengths where this temperature emits. So you have, normally when you have low temperatures, you use then the microbolometers, long wave infrared cameras. But when you have then higher temperatures, like from 250 to 800 degrees, you can also use then the sphere camera to detect this one. And you all know when you have steel or whatever, that is very hot, it's 1,200 degrees. You can't see that with your eyes, and it's too bright for your eyes normally. Then you can use them really with visible cameras. The point is here that with the sphere cameras, when you want to really measure absolute temperatures, you have to calibrate the camera per aperture of the lens and per integration time. Normally in the microbolometer cameras you have only one aperture and continuous readout, so there's one integration time. So that is that easier, but when you want to see only in this glass inspection, when you want to see difference in the temperature, then you can also detect it relative and not absolute. And therefore you didn't need any calibration. So that is another point here is that this hyperspectral imaging is also one very good method, combines then digital imaging with spectroscopy to obtain detailed information across multiple wavelengths or multiple ranges of this electromagnetic spectrum. And you can use this hyperspectral imaging in different applications here also, in recycling and plastic sorting is a very wide range, in geologic and mineral inspection, and pharmaceutical quality control, and also in food and agriculture, and also in medical and disaster diagnostic you can use this spectroscopy. And so, because each inorganic material has a different chemical composition and crystalline structures result in a unique spectral response corresponding to specific light absorption characteristics. And here you see an image, an illustration of 5 different plastics, starting with 1,000 nanometers, and you see from 1,000 to 1,700 nanometers here. You see then, you can detect then the different plastics. When you see over the whole range, you can count the minimums and see that difference in the sort, in the plastic sort. And so you can really, over the whole range, you can really separate then these different plastic sorts. On the other hand, as higher the wavelength, as better the characteristic of this material. And so this, you see it also here in the range from 1,700 to 2,500 nanometers, you have more characteristics in there. But normally in this range, the sensors itself are much more expensive. And normally when you have recycling industry, that's also cost-sensitive area. So mostly they want to use this range because it is a question of costs there. So that is, I think today there are different lessons about hyperspectroscopy, so you go more than in detail. so I didn't want to expand it here. My conclusion here is that we have three technical differences between sphere and CCD and CMOS cameras. One is the detector that we have here, these INGAs, also indium gallium arsenide detector. There's silicon detectors. We have the cooling capability needed to reduce the noise. And we need then more intelligence, the advanced image correction features inside the camera to have a real good image here. So take sphere into consideration and explore your application with new eyes. Some sphere cameras offers new physical effects in the shortwave and the infrared spectrum. So normally you have to think about absolutely different. You see that on water. Water is a good characteristic. Water is transparent and visible and black in sphere. So you have to think about different. So when water is black, so you can also measure then on the contract, you can measure the moisture in plants, for example. So for agriculture industry, it's very important to do that. So you have to think different in sphere. And so that sphere helps you then improve the yields in terms of quality as well as productivity. So I show you that you can have a higher speed for this electroluminescence or photoluminescence method, or you can see like water or whatever, you can totally different. So this is hyperspectroscopy when you have, for example, the right database with different spectrum. You can also detect and you can measure the speed of fruits. So that's totally different. So, yeah, so that is what I want to show you. That is in short, only in short overview, give you some ideas what one can do with sphere technology. And you can visit us on our booth here in this hall at 1905. And so when you have, or you can call me if you have some detailed applications or whatever where you need help or more detailed information.